which you already know this is going to be the talking about energy research. But you know our goal is to talk about sustainable campus and sustainable cities, and you're going to see some research projects that address that at various scales in these three presentations. Moving along. Next. And as you'll see here in these presentations, and I think in the previous sessions, you heard about the collaboration between the faculty, the staff, the students, both on campus and in other places. And this is where one of our speakers will talk about schools, for example, outside of the campus. But all of those have this general goal of sustainability and using the campus as a model. Moving along. You've now know we're at the last session at this afternoon. So we hope that at the end of the session, you will fill out the survey form. So please help us so that we can design a better workshop next year. So let's move on. We've got three speakers, beginning with Cori Jackson, and then Theresa Pistochini, and then Josh Moorjohn. And I am not going to say anything else except to remind you that if you want to learn more about these speakers, you go to the website. And all of them, I can assure you, have a fascinating history. So I urge you to do that later. But right now, let's listen to Cori speak. Cori, go ahead.
Perfect. Thank you, everyone. Welcome to the last session. My name is Cori Jackson. I'm the program director at the California Lighting Technology Center at UC Davis. And as Alan mentioned, we're going to talk about some work that we're doing here on campus. We've been very fortunate to be able to use the campus as a living laboratory. And the project I'm going to talk about today demonstrates just how that works and what that benefit is. So the project that I'm going to share with you today is focused on integrated building control systems. So what this means for us is we started, of course, in the lighting world. And what we now are looking at is taking control systems that were once just exclusively used for lighting and combining them due to interrelated effects among things like lighting and HVAC, combining into an integrated control platform so that we can control multiple systems within the building in a more efficient way. Instead of doing several individual types of controls, we're combining through essentially a central management system to do things that are a little more sophisticated with our controls. So one of these projects was funded by the California Energy Commission starting in 2017. So we're just wrapping this project up. And the goal of the project was to develop an integrated control package focused on retrofit. So existing buildings are the largest component of the building stock in California. And the commission was very interested in finding solutions that would work for existing buildings. And so our project, we partnered with the UC Davis campus to demonstrate a system that looks at integrated control for lighting, fenestration, which is a little unique, we'll talk about that, and HVAC. And the goal is to maximize performance of those systems in terms of occupant comfort and energy performance, and then do that with commercially available technologies. So we wanted to do something that we could take off the shelf, combine in an efficient way, and demonstrate. So our system, we call it an integrated building control system, so IBCS, very basic. Our system uses a couple of different strategies that most people would say are pretty common sense. So our building control looks at strategies for when the building's occupied, and we look at strategies for when it's vacant. But we're controlling the lighting, the fenestration, the HVAC, all of those based on the collective impact of those systems on the building. So lighting can contribute heat gain to the building. We could open operable windows to cool the building when it's cooler outside than inside. So looking at all of these things in a more holistic way. And this slide, apologize, it's a bit busy, but the point here is while we're looking at only 3 or 4 systems, there's a whole host of different kinds of systems and inputs to the system that you can do. And not every portfolio of components is appropriate for every building. We've partnered with the John Muir Institute for the Environment on campus, and I'm going to show you a picture of that building. And in that building, we're looking at HVAC, fenestration, and lighting, with the future potentially adding plug load control to that. And so in order to do that and create this living lab on campus, we've instrumented the building with a number of different kinds of sensors, in addition to a number of different types of new hardware to demonstrate the concept. And in order to get all of those things to work together, we use what we're calling a system integrator. And this is what many people would, say is a building management system, but it's a unique device that bridges all of the different individual systems together, and they may be speaking different languages, using different communication protocols. So it takes in all of that input, it takes in sensor input. We have a weather station at the building. It's taking in all of this information and allows for custom programming to develop control algorithms that are then responsive based on, right now, the input from those sensors and from the outdoor conditions. The particular system we're working with, you can see here on the slide, is called a JACE. It's offered by Tritium, and it basically forms the heart or the brain of the entire system. And so we've taken this technology and we've installed at a building on campus that is called the barn. And back in the day, this building literally was a barn on campus for livestock. And since then has been remodeled a number of times, most recently as part of our demonstration work here in the last year, which wrapped up in September, where we replaced all of the windows with operable windows that are actually controlled as part of the system. We added in new lighting, dimmable LED lighting. We added in new HVAC system. And then we tied all of that together through the Tritium JACE, and it's controlled by some novel control algorithms currently that we've written for the system, and it's been programmed in there. So while we're looking towards existing buildings, in order to demonstrate the concept, we went ahead and replaced a number of these components with new products that we could control and really treat this building as a living laboratory. So this is the first phase, is to retrofit the building, both in terms of sensors and equipment, in order to use it for future projects. And so we're looking forward and talk about one of those projects coming up and how we'll use the building. In this image, you can see we have a number of different sensors in the building. We've retrofitted approximately, I think, 20 spaces in the building itself, and there's a variety of different sensor types, bringing in illuminance, measuring illuminance outside, measuring CO2, particulate for air quality, temperature, of course, and occupancy within the space. And all of that information is then being utilized to make control decisions for the building as a whole. So some of the performance metrics that we're looking at to quantify how this building is operated. Number one, we're doing some subjective work to understand things like luminous comfort, thermal comfort, indoor air quality. This project was conceptualized and funded pre-COVID, unfortunately, and so a lot of the work that we planned for an occupied building has not been realized at this point. So that's unfortunate, and then we'll be working around that. But we have tabled the subjective work now and are looking at the quantitative work related to lighting energy, HVAC energy use, based on occupancy, illuminance, temperature, all of those things that I just mentioned. And then trying to understand the economic impact, simple payback, and things of that nature. One of the interesting things looking ahead, and this will be one of the first projects that we'll use this living lab for, is in California. We are going through a load management, a load standards rulemaking with the California Energy Commission. So this is separate than the energy standards or the appliance standards. This is actually work that the commission's doing to make recommendations to the California Public Utilities Commission for real-time pricing. And they're creating recommendations for a digital signal that will convey hourly or even sub-hourly pricing information, as well as GHG composition. And so with the onset of real-time or dynamic pricing, where things are changing on an hourly basis, we can start to do some very interesting things. And one of the things that's planned for this building—
I just want to warn you, excuse me, 1 minute left, Cori.
Okay, I will whiz through. One of the things that is coming down the pipeline has a simple name, predictive scheduling, but it's actually based on the mathematical optimization techniques. And so we're taking basically a building design, and we're creating a linear programming model. And this is a mathematical concept that comes out of operations research. We're basically creating models that are estimating a very complex nonlinear work or nonlinear interrelationships between all of these building systems that are going on. We're estimating them with linear approximations, and you're basically creating a linear program with hundreds, even thousands of variables and hundreds and thousands of equations, and you can solve that system to optimality. And when you solve it, you result in a schedule. Right now we're doing 24-hour scheduling. You can result in a 24-hour schedule for every system that you've built into your model that will minimize cost in GHG. So it's a simple concept, but it does take a lot of work. Right now, we're looking at, we're going out onto the web and we're pulling weather information and real-time pricing from a couple of utilities that are already broadcasting their real-time price information. One is Commonwealth Edison out of Chicago area. So we're pulling in their real-time pricing through an API and using it to do this predictive scheduling to demonstrate how this concept would work. And so,
Cori, I'm going to have to call time.
I have one word. This is the most important part. Up in the red circle, this is a picture of the building. We're looking at HVAC, cooling, and lighting, several modes for each system. When I ran the model on September 2nd of this year, at the time, Commonwealth Edison was predicting a negative electricity price. And so the schedule upped the HVAC and lighting to full on within and kept the building within constraints and was actually serving as an electricity sink for the system because there was overproduction. So a lot coming in and a lot going on, and we'll be able to do a lot more predictive and optimized control in the future. So thank you.
Thank you, Cori. And I'm sorry to have cut you off because I think you had about 4 or 5 other important points. Maybe some of the questions will bring them up. In the meantime, let's move on to the next speaker, and that is Theresa. Would you like to take over? And
yes.
Let's get the
Thank you,
up.
Alan.
All right, go ahead.
Just for my pacing, can you tell me what time I'm scheduled till?
You have 10 minutes, and I'll give you a 2-minute warning.
Okay, thank you.
Yeah.
Hi, I'm Theresa.
Do you want to turn your webcam on quick?
Oh, sure.
There you go.
There we go. Okay. Hi, I'm Theresa Pistochini. I'm engineering manager at the UC Davis Western Cooling Efficiency Center. And I wanted to share with you today a project we've been doing to quantify refrigerant use for maintenance and operations at a school district. So the goal of our project here is to learn a little bit more about the annual refrigerant amount used in small air conditioning equipment. There's been a fair amount of quantification and study in California on refrigerant leakage from like large chillers and big systems, but there isn't much or any firsthand field data on small AC equipment, so that in the category of less than 50 pounds. And so what we did here was design a firsthand data collection method. And our goal was to look at total refrigerant use, but also to disaggregate refrigerant use between R22 and 410A. And then at the end of this, we want to compare what we learned to other existing sources of refrigerant use data assumptions. So our overall approach, this hinged on a great partnership that we've been forming with the Eastside Union High School District. Really just want to recognize the support of Roger Silvera there, who's their facility manager and has been just a really great partner. The district has 19 campuses and 2.4 million square feet of floor area. And we looked over this particular analysis period, which is just slightly over 4 years. The reason for this analysis period is that March 1st is a time at which the district decided to start to manage and inventory some of their own refrigerant to protect against a concern for rising refrigerant prices. So it's basically just an opportunity for us to essentially start counting from that time. The district has approximately 1,800 pieces of HVAC equipment, and the equipment is district owned and maintained. They have 4 maintenance techs who primarily do inspections and change filters. And then they have 2 repair techs who have more training in HVAC repair. And then the district hires contracted services as needed, basically based on bandwidth, right? Like if they need additional help. So this is our overall approach. We basically analyzed the refrigerant used at the district for those 4.25 years. And then we added up all the refrigerant charge at the district based on their entire inventory. And then we divide one by the other, basically, to get at an annual use rate for refrigerant, a percentage use rate for refrigerant. So basically what we did is we cataloged all the refrigerant purchased and used by the district facilities technicians. We also, and this just involved go through hundreds and hundreds and hundreds of pages of receipts that the accounting department provided to us. So then we also added up all of the refrigerant provided by the HVAC service contractors. We accounted for any refrigerant remaining in inventory today. We subtracted any refrigerant recycled that we had receipts for. And then that basically gives us the refrigerant used. On the flip side, we cataloged the entire charge at the district. So we basically use an online inventory software that they have called the Kita Box. And we went through and we pulled all the HVAC system data and we looked up the charge for each HVAC system based on the model number. We were able to do about 75% of this without looking at the equipment, but about 25% of the equipment in order to get all the information. We did an on-site inspection. And basically more than 99% of the time, we were able to really confidently conclude the charge on the equipment. A very small percentage of the time, we had to essentially make an educated guess based on the size, like we just couldn't get a model number off the equipment. So just a little bit about, I think this is very interesting to really look at, to give you an idea of what type of equipment the district has. So the equipment is basically R22 and R410A, which you would expect. There's the split is roughly 65% R22 and 35% R410A. And we're looking at primarily rooftop units with some wall mounts, which tend to be more common in school facilities, and then a smaller percentage of split systems. So if we basically look at all the equipment and we look at the charge of that equipment, and then we analyze by year, you can see, as we would expect, R410A was phased out January 1st, 2010. So you can see here that there's no R22 equipment manufactured after 2010. I should mention we got the manufacturer year from the serial number of the equipment. And you can see here then the R410A equipment picked up. Because we're analyzing these last 4 years, the charge of the R22 equipment is dropping, right? Where we assume here that any 410A equipment replaced a piece of R22 equipment. So over the years, we basically estimate the R22 charge at the district from 2016 to 2019, and then the same for the R410A, assuming that this new R410A equipment replaced R22 equipment. And so then getting to the results, this is essentially an accounting from all of our receipt cataloging. And you can see here over the years, the district used 586 pounds of R22 and 80 pounds of 410A. And if we calculate an average per year and we divide that by the total refrigerant charge at the district, you can see here that the annual leakage rate for R22 we estimate at 2.8% and for R410A at 0.7%. And that obviously leads to some interesting thoughts, such as why are these different? Is it that the R22 equipment is just, is it that there are manufacturing differences in equipment manufactured with 410A because it operates at higher pressure? And those are all not, unfortunately, those aren't things we can answer per se in this study, but those are just some interesting questions these results raise. Overall, these results are lower generally than the industry estimates. I guess I should say than policymakers estimate. We're able to also go through every single service record at the district in terms of like when a teacher files a complaint, not a complaint, but when a teacher reports that an HVAC system is not working, it creates a service record, and then an HVAC technician goes out and looks at the equipment and makes a repair, and then they document their repair. And so we were able to go through all the repair notes and try and provide some qualitative information as to what types of repairs are most associated with leaks. And you can see here that we basically categorized every time a technician mentioned using refrigerant in some way, right? So we searched for words in the service. Yeah, this is my last slide. We good?
Good.
We basically searched the service ticket database for words like Freon, R22, 410A, refrigerant, those types of words, and then we basically went ahead and calculated all this. And what you can see is there's a couple of themes. We did notice a lot of cases where refrigerant was added, but there was no record of a leak repair being made. Essentially, just refrigerant added to replace lost refrigerant, but no identified leak or repair. We did see a lot of indications of service ports leaking, of Schrader valves leaking. And then the other most common repair is just a technician noting that they made a repair, but they didn't specify the location. Also over here, we can see like how common is it that an equipment is over those 4 years serviced with refrigerant more than once. That was actually very uncommon. Most of the time, there was only one record associated with a piece of equipment. Finally, we're working on a publication of this study in a peer-reviewed journal. In the meantime, if there is anybody listening that finds this intriguing and might want to participate by adding their data to this study, particularly, we didn't find any VRF systems of significance in this study, and it's an area of research interest. So if there's anybody on the phone listening that would like to participate, please drop me an email. We'd love to talk about it more.
Thank you, Theresa. There's some intriguing results there, and also just the creative research methods. Who would have examined receipts to figure out leakage rates? But there you go. So
I'm not sure I recommend it. It's quite tedious.
Well, maybe there'll be some more questions about it. Josh, it's your turn to talk about UC Davis.
Here I am. Yeah, let's get started. So the both Theresa and Cori are part of their teams are part of the Energy and Efficiency Institute and the centers there that do research like they've talked about. Much of it very applied research, and I'm part of facilities management in the operations at the campus. And so I'm going to talk about projects that we're doing on campus. So a little different, but a lot of them have overlap because we partner with the Energy and Efficiency Institute researchers on a lot of these projects. So I'm going to kind of focus on ones that are related to research. The title it's not a joke. I'm really going to talk about cows, cold water, and campus Wi-Fi. That's Jules the cow. You'll meet her soon. I'm going to start with talking about cows. So we have a cow-themed thermostat app for participatory thermal feedback. We have a cold water battery or a thermal energy storage tank that is doing a lot of cool things on campus, especially lately we were able to turn off 12 megawatts on our campus to help out the grid and save some money. And then we also have campus Wi-Fi that you might have heard about in the lunch session or the education session. And I'm going to talk a little bit about what we're doing with that. And as a bonus, I'm throwing in there hot water. We're doing a large hot water project as a pathway to electrification. So I'm going to jump into those, try to make this quick so we have time for questions. So as far as the cow, well, this is Jules the cow. It's something our engagement team came up with. The students love it, but it's a thermostat web app that is essentially, the tagline is "You're smarter than a thermostat," and we tell students that we want their feedback. We want to engage the people in the building. One of our kind of core tenets is that the buildings are there for the people, and so we want to make sure we keep the focus on the people in the buildings. And one way to do that is to get direct feedback from them. So we have this app where we are able to get feedback from people in the buildings. A lot of times it's students in classrooms that don't have another way to express their comfort or discomfort levels. And we also, beyond engaging them, we want to actually identify problems in the buildings. And you know, we're speaking for facilities, we're not in every building all the time. So we really want to leverage the people that are out there. And then we want to also improve comfort and productivity. That's what we're here to do, is support the mission of the university. The research part of it is actually been pretty fascinating because there's a lot of really interesting behavioral research that comes out of this. And so we've published a number of papers. You can look them up. There's one there about using this participatory thermal sensing, and it's actually been a very effective operational tool for us in facilities as well. So I just want to put that out there. The next one I'm going to touch on is the cold water battery, and that's our thermal energy storage tank. As part of our chilled water system, it acts as a thermal battery, and it holds 5 million gallons of cold water that we use to cool the campus buildings. It's charged by 4 large chillers in the adjacent plant, and it's part of our overall district cooling system for the campus. As far as research, recently we've had a team of grad students working on optimization for this system using this thermal battery, and one of them was Devin. If you heard her in the last session, she's with the Energy Graduate Group, and then some graduate students from chemical engineering as well, and they've been working to do the modeling for our chiller plant and come up with algorithms that we're actually using now to inform and educate our operators with visualization that they can use to optimize the charging and discharging of our tank based on real-time or day-ahead market rates. So just to talk through one example of how this played a big role recently, back in August, if you were on the lunch session, you heard about the challenges that the California grid had in August, and there were some major heat waves. There were some rolling outages, and people were being asked to do what they could to relieve some of the pressure on the grid. Our campus actually was able to do a significant amount of that because of this thermal battery we have. So I'm going to just walk through this trend real quick, even though there's a lot going on. You can see the rate in the green, and the rate is increasing at this peak time, which if you know the California grid and the duct curve, right after the sun goes down and everyone's still using air conditioning, the rate was spiking to a really high rate, which we probably haven't seen for a while, about $800 a megawatt hour, and even higher maybe on some of the other days around there. At least that was the forecast. This is a forecast rate. Actual ended up being a little bit different. And then we were using that to run our chillers. You can see we're running all 8 chillers that we have at that time. Our electricity load was high. As soon as the rate started to climb, we were able to shut off all of our chillers, and essentially 12 megawatts of power for the campus, which our peak megawatts is around 40. So this is a significant portion of our campus load. We could shut off for the time period that the grid was maxed out, and also some significant savings that could come with that. So that's a really interesting project we've been working with the grad students on, and it's an ongoing project. Campus Wi-Fi. Real quick, I want to just mention some other campuses are doing this as well. I know we've been talking with University of British Columbia, Vancouver for a while about this, and they've got some great experience and have taught us some. But what we've been doing is we use the number of connected devices. So any device that's connected to the campus Wi-Fi, we're able to grab those numbers from our IT group. They track it. They don't track who's connected. They just track how many people are connected to every access point on campus. And then we can aggregate those by building, and we can aggregate them at the campus level. And so we're able to see really interesting trends during this pandemic. You can see this trend here is showing back to the beginning of March, and the orange is what we've modeled as the typical occupancy based on this connected devices count, which is typically over 30,000 connected devices on campus, which approximates the number of people showing up every day on campus. And you can see the blue is the actual when campus shut down for the pandemic. It went down to less than 10%, and it's stayed that way. Recently, last week, the students came back to live in the residence halls less than normal, following a lot of precautions. So that number's up at about 6,000 or just under 7,000 on campus. But we're able to see that kind of trend, which has been a lot more useful than we ever thought it would be. We can do it at the building level, and we use that data with our energy engineering team to optimize scheduling. You can see HVAC schedule shown in the red here when it's on and off, and looking at the Wi-Fi data, you can see there's many days in this building where there's HVAC systems running and nobody's in the building. So we're able to optimize scheduling, not yet doing it in real time, although we're doing some alerts in real time, but we're able to program weekly schedules based on typical occupancy rates, and same thing with holiday shutdowns. But we're still working on more that we can do with this. Alan Meier's actually been leading a research project called Putting Vacant Buildings to Sleep, which is based on this idea.
I'm not going to let you talk about that because you only have 2 more minutes.
Yeah, I'm just going to mention it. And so we've had 2 energy graduate group students do their master's theses on this as well. And I'll just throw out there that we've found this Wi-Fi to be, this data to be very useful in the COVID period. I've been able to send reports to our administration on at the building level, how many people are in each building each day based on, compared to normal pre-COVID. And that gives them an idea of which buildings are more occupied, and that can also help us prioritize how we're doing operations for those buildings. Also useful during the smoke events when we had to shut outside air down, and we could look at which buildings were more occupied. Last one is just this hot water bonus project I'm going to throw in here because we have this goal of carbon neutrality by 2025, and the big challenge for us is to get off of our gas-fired steam system. So going to hot water allows us to go to heat recovery. A lot of other campuses are doing this as well. We're putting pipe in the ground right now, and I'd love to talk more about it maybe another time, but full ultimate goal will be electrification with either geo-exchange and air source heat pumps. And there's a lot of projects we've done on this, and we'll probably be doing a lot more research around this as well. That's it.
Thank you very much, Josh.
Yeah.
Now I think I'll open it up to questions from the audience. And help me, Ali, are you going to read the questions or should I? Well, since there's silence, I'm going to read the first question. I think the first one went to Cori. And this was about, let me expand the question a little bit so that I can see it a little better. Can what you were describing with the electricity the management and total energy management system for the building be done in a cost-effective way? For example, when compared to the price of just using smart thermostats like the Pelica wireless.
Right. Thanks, Alan. In certain applications at this early stage of the research, it can be cost effective. A smart thermostat is a mature technology, and costs for that are substantially lower because of that fact. And it does a more limited set of measurements and controls. So when we start looking at something like an integrated system where we're controlling multiple systems, it's sort of an apples to oranges at this point. But short answer, under certain applications, and we expect those applications to, the number of those applications to grow going forward as this matures.
Okay, thank you. I just want to remind you that if you want to put in a question, you probably know that there is an option on your little dashboard to put in questions, and I'll try to group them if necessary. So just because you're the last one in writing it doesn't mean your question won't be answered. Josh, how do you control the growth of organisms in the cold water energy storage tank?
Okay, that's an interesting question. Well, it's a closed system in that it's circulating, but it is open to the atmosphere within the tank. And I mean, it's cold, so it varies between 39 degrees and 60 degrees Fahrenheit. So there's not a lot of growth, but we do also have filtration on it. And at one point, I know in recent history, we've had to do some biocide treatment on it when there was some growth. So it's just something we monitor, but basic water treatment can prevent that if you keep up on your water treatment.
Okay. Question for Theresa. Did you include all kitchen refrigeration equipment or just HVAC?
We only looked at HVAC because that's where it seemed like the strongest research need was. There are other studies that have looked at refrigeration losses, and the school district is, their refrigerant is primarily HVAC. There's a few, most campuses have a kitchen, but it's not as significant.
Just a follow-up question from the moderator. Those leakage rates, are those similar to what the literature has reported?
They're actually a little bit lower. The EPA vintaging model, I think, assumes about 5% annual leakage, and we had, the older systems at 2.8 and the newer systems at 0.7. So that's definitely lower than what's out there currently.
Okay. Here's a question for Josh. How do you save energy, Wi-Fi energy? Do you switch it off? So you're using the Wi-Fi to control the buildings, or at least to be aware of the buildings are empty or not, but the Wi-Fi system itself uses energy. Do you control that or try to?
Yeah, so I was talking about, like you said, using Wi-Fi signals and connections to know if the building and the systems in a building could be turned on and off. In general, I would say that the Wi-Fi power usage is small compared to a lot of the other systems. But as you know, Alan, we're working on a project where things like whether it's Wi-Fi, routers, network closets, and especially we found audio video equipment can amount to a significant load in some of these buildings, especially if it's something like a classroom that doesn't have a lot of other process equipment and may have everything shut down when it's unoccupied. And some of these loads do amount to something significant. And we're still working on exactly how all these systems can be turned off. So we'd love to follow up more on that if they have more questions. I'd like to answer the one about the steam system that just came in.
All right, go ahead.
There's a question about how with the Navy bases, decentralizing steam plants and installing individual condensing boilers has yielded massive savings. So why did we use a centralized heating system? And that's a great question. We've actually spent a lot of time studying both sides of that. I think that the big answer is that is steam. Getting away from steam was the big savings for us. So a centralized steam system, I think, is a really bad idea in terms of energy, because like in our case, we have over 20 miles of steam and condensate pipe. Steam's at 350 degrees. It loses anywhere from 30 to 50% of the energy just in the distribution system. So huge energy waste. And so I could see how putting localized steam plants could get that savings. But when you don't even need steam, to do your heating, I mean, most heating that we need is that we've found buildings can take 155 degrees, even if they're designed for 180 degree hot water systems. They only need 150 or 155 to do their heating at peak for the most part. And so we're able to go to a much lower heat source, which then opens up the door to things like heat recovery, where you can recover heat from your chilled water system, which is what we're going to be doing, and use that and make the whole campus way more efficient instead of generating steam with gas. So if you can get away from steam, I think that's a huge step as well. And yeah, go ahead, Alan.
If I can direct a question to, I think it's Cori. How do you select where the sensors are installed in the space being tracked?
Yeah, it all depends on the sensor. So every kind of sensor and every sensing strategy, there's often multiple strategies that a daylighting sensor, for example, would use. It depends on the specs of the sensor on where the best placement is. So, I gave the example of daylighting. When it's an open loop system for daylighting, we want it looking out and reading the daylight contribution from the outdoors. A closed loop sensor we would want in a place where it could read all the lighting contribution, including the electric lighting. So really just depends on the exact kind of sensor and the mechanism that it's using for its sensing strategy.
Great, thank you. Here's another question for Josh. When you get away from steam, how do you serve loads like autoclaves?
Yeah, good one. Well, what we've found, because we are in the process of turning off steam in buildings, we found that it kind of falls into different categories. Some steam loads don't need to be steam, they just need heat, and they're using steam because steam was there. And that could be even in the case of autoclaves. You can have an electric, or it may still need steam, but you could have an electric one if it's only used once a week, something like that on a small scale. We found cage washers, which are using steam to do their cage washing, actually only need hot water, but they use the steam to heat the hot water. But we're able to have boilers that just make hot water instead. We have steam dryers that we've replaced with electric dryers. There's challenges around the electric system and having the electric capacity, and that's something you have to look into. But in pretty much every case, we found that there's a more efficient way to meet a steam need or heating need than to have a distributed steam system. So even if you have to put in condensing remote boilers to serve that load, that's a more efficient way to do it.
Thank you. I have a question for all of you. All of you mentioned using graduate students and other students to help you do the research. When are students good to use and when are they maybe not the best choice of expertise to apply to a problem. Yeah. Who wants to grab that one?
This is Cori. I can answer, at least from my perspective. I found, at least with all of our projects, there's always an opportunity to use a graduate student. It may not be, we've had to search for graduate students with certain skill sets, but I think there's always a learning opportunity within any project that can benefit the students. So I can't really think of a time when we haven't benefited from including undergraduate or graduate students on our project.
Yeah, I would agree. I think every time's a good time to use a student. It takes a little bit of work sometimes to get them up to speed, but you know, I think they learn quickly and they get a lot out of it, and that's part of why we're here as a university. And they do great work, so we try to use students as much as we can.
I will chime in and say that it was actually not me that went through the 1,000 pages of receipts. It was an undergraduate student. So that was a great time to use the student. And actually, but though, we're not stopping there. He's helping write the publication as well. So.
Yes. Let's see. Are there any other questions that I missed or you want to expand upon on the ones that are submitted?
I can address real quick the question about high temperature heat, because even on hot water, yeah, some buildings we're going to have trouble with lower temperatures. We're going to initially run our district energy system at 155, hopefully even 150. We're not sure yet how low we're going to be able to go. We'd like to go lower, but it's just going to be a process to deal with building issues. Mostly the buildings we found that can't run at that temperature, it's not because they need 180 degrees, it's because they have some other problem, an air system problem or dirty coils or some other issue that you have to deal with. Sometimes it takes investment, so it might take some time.
Excellent. I think we were supposed to end at 10 minutes before the hour. So unless people have other questions, I'm going to call the end of this session. Uh-oh, there's one more question. Hang on a moment. Let's see. Somebody said yes, one more, but didn't provide the question. How can we track the ongoing work? That's a very nice. And then he says, this is exciting. How can we track this? So where do you publish your results? And probably each of you should answer that.
Yeah, I guess I can say follow our website, especially follow the Energy and Efficiency Institute's website, energy.ucdavis.edu, and we'll try to keep people updated. Ali might be able to speak to an email list where we'll be keeping people in the loop about next year's workshop, which we're looking forward to having in person, hopefully, and meeting some of you face-to-face as well.
I was going to say, make sure to subscribe to the EEI newsletter because that links to all of our websites. And Josh, I'm not sure if we've included your updates in that newsletter, but if not, that would be a great thing to do.
Okay. Sometimes Ali gets it.
Yeah, I'd echo that. CLTC has a newsletter. We often, publish findings, new things there. A majority of our funding comes from the California Energy Commission, so you can always go to the commission website and do a search on reports from our institution or our department. And then our website's always a good place to track our ongoing research. And of course, emails to me or to our engineering director, Keith Graber. Any of the staff are happy to speak with people about our research.
Perfect.
It looks like Ali just chatted that link to the chat.
Oh, yep, there she put it in there. I'll give everybody a moment to enter it, and I think that's a great way to end, except to remind everybody that there is a survey that we'd like you to fill out so you can make some suggestions so that we can improve for next year. Thank you for participating. It's a pity we can't see each other's faces and have a little bit of a physical interaction here and a little bit of gossiping and making more friends, but I'm sure it will happen again next year. So thank you very much. And I'm going to shut down right now with, if I'm permitted to.
All right.
Yep.
Thanks.
Thank you, everyone.
Yeah.